Okay, so let's resume. So we are at a good point. So now let's develop our theory, our proof method. And what's the key insight for our proof method of how to obtain machine verifiable linearizability? Here it is. Machine proof systems, meaning software proof systems, they're good with certain things. What are they very good at? They're very good at verifying simple algorithmic invariants. So, for instance, if you give a software proof system your algorithm and the inductive invariant that your algorithm satisfies and the proof that the algorithm satisfies the inductive invariant, the inductive proof, then the system can be convinced, if your proof is correct, the system can be convinced that your proof is correct. It will say, yes, I agree that the algorithm you gave indeed satisfies the inductive invariant that you stated. Okay? So, that is what they are good at. So, that is what we should be able to, that is what we have at our disposal to use. What do we want to do? We of course want to prove that an algorithm satisfies linearizability. But then showing that an algorithm satisfies linearizability is not simple, because you have to show the existence of linearization points for every run, and that is not easy. So, the machine is not directly useful for that. So, we should somehow do this, which is what we want to accomplish. We want to do this using this ability of machines. And how do we do that? We do that, this is the idea, we reduce the problem of proving that a given implementation is linearizable, that a given implementation, a given algorithm A is linearizable. That is what we want to do. We reduce that problem to proving a simple invariant of a transformed algorithm A star. So, what do we do? If you want to prove that this algorithm A is linearizable, we transform it. I have to tell you how to transform it, but we transform it into a related algorithm A star such that A star satisfies a very simple invariant, which you can verify using the proof systems, if and only if this algorithm is linearizable. So, you are reducing, you are transforming the question of whether this algorithm satisfies a linearizability to figuring out whether a transformed algorithm satisfies a simple invariant, which can be done using machines, using proof systems. So, that is the idea. So, of course, that raises the question of what is this transformation going to be, and to understand what this transformation is, the main thing to remember is that A star, this transformed algorithm, maintains possibilities. Okay? So, A star is like the original algorithm, but in addition it maintains a variable which stores in it possibilities. So, what are these possibilities? Well, let me explain that slowly so that we all travel together. By the way, the intention from here is that we all should be able to follow every bit of detail. So, if there is any place where I am not clear or you are left with a question, be sure to ask. Okay? So, what are possibilities? So, I am first giving the intuition for what I mean by a possibility. So, take this particular run. There are 4 processes, pi 1, pi 2, pi 3, pi 4. Pi 3 has not initiated any operation, but pi 1 and pi 2 have initiated NQ operations, and pi 4 has initiated a DQ operation. And if you look at time t1, all these 3 operations are still ongoing. None of the operations has finished. Pi 3 on the other hand, as I said, is idle. Okay. So, let us ask the question as to what are the possibilities at time t1. So, first intuitively, what do I mean by a possibility? What I mean is, what is a possible state of the queue at time t1? What is a possible state of the queue at time t1? And in addition, not just the state of the queue, what is the possible status of each of these processes? For instance, take process pi1. Pi1 has an ongoing operation. Has that ongoing operation linearized before time t? Well, isn't it possible that that operation has already linearized? Well, that's a possibility. Isn't it possible that that operation has not linearized, has not taken effect yet? That is also a possibility. Agreed? So, a possibility is going to encode the following information. A possibility is going to state what state is possible for the queue, as well as what is the possible status of each one of the 4 processes. Each one of the processes, which is 4 in this case. That's what a possibility is going to summarize for you. So, let us consider one possibility at time t1. So, at time t, let us assume that the queue was initially empty. If the queue was initially empty, is it possible that none of the operations has taken effect so far? Of course, that is possible. And in that case, what would the state of the queue be? It was empty in the beginning, so it would still be empty. And if the operation from pi1 has not taken effect yet, then what is the status of the operation pi1? That is given by this triple. And this triple is simply saying that pi1 has an ongoing operation, and that operation is nq. 5 is the argument of that operation, and the blank here in the third component of the triple says that this operation has not linearized yet, and therefore has no associated response yet. It is still, the response is still pending. Likewise, pi2 has not linearized yet. Pi3 is blank, 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 and the blank here states that it has no ongoing operation at the moment at time t. So, this is a possibility at time t1. Okay? And pi4 has a dequeue operation. Dequeue operation has no arguments, so the second component is blank, and the third component is blank because the dequeue operation has not taken effect. So, this possibility captures the notion that none of the operations might have taken effect yet, and therefore, the resulting state of the queue could be that. So, do we understand how that is a possibility? But that is only a possibility. There are other possibilities. Here is another possibility. Here, this possibility is capturing the notion that pi1 could have taken effect, that black dot. Pi1 could have taken effect, and if pi1 took effect, what would it have done? It would have changed the state of the queue to 5. It enqueued 5, and then it took effect. So, what would the response for the NQ5 operation would be? It is ACK, and pi2 has not taken effect, and pi3 of course has no operation. Pi4 has not taken effect yet. So, this captures the notion that pi1 alone has taken effect and others have not, and in that eventuality, the state of the queue would be this. So, this is a possibility. Are we together? Okay. Here is another possibility, and this captures the notion that pi2 alone could have taken effect and others did not, in which case the state of the queue is 9. This captures another possibility. This possibility captures the notion that pi1 and pi2 could have both taken effect, and in the order NQ9 first and then NQ5, causing the state to become 9,5, and pi4 has not taken effect. This captures the notion that again pi1 and pi2 could have both taken effect. No, it captures the notion that pi1 and pi2 could have both taken effect, and the DQ might also have taken effect, and these two took effect perhaps in the order that perhaps in the order NQ9 and then NQ5 and then the DQ took the first NQ'd item 5. So it captures the notion that things could have occurred in that order, leaving the state in 5. So that's another possibility. Here is another possibility, and this says that, well, NQ9 alone among the two NQs may have taken effect, and then the DQ might have followed it. And I think the dots were put incorrectly.
No, it's okay. You simply NQ9 and then you DQ9.
But I put the DQ dot there.
Sorry.
Okay, this dot should have been here. Okay, yeah. But pretend that it was there. So that's a possibility. All right. So do we understand what a possibility is? By the way, I showed 6 possibilities. There are more possibilities I could have shown, and the point is not to be exhaustive. There are probably 16 possibilities by time t1, but I showed some. But we understand what a possibility means. Possibility, therefore, captures a summary of what state the object could be in and which among the ongoing operations may have linearized, and if they did, what their associated response is. Right? Here I showed a simple run that barely began. But imagine a run of these 4 processes where they have issued billions of operations and completed billions of operations. Even so, at the end, there would be, of course, some number of possibilities, but each possibility would still be capturing only the summary. And what is that summary? If at time equals to 1 billion AD, by which time these fellows have completed trillion operations, the summary would still say, at that point in time, what is a possible state of the object and what is the possible status of the ongoing operations at that point in time. Not about all of the various operations that completed way back in the past. No, just about what is ongoing at that point in time. Are we together? So this is the central notion. A central notion.
Prasad, what do you do about operations which have completed?
They are not part of the possibility. We have forgotten about them. This is the only thing we are tracking. This is the only thing we are tracking. And what is important to remember or to note is that if I said, imagine that this was a long run where billion operations took place. If I said this is a possibility at time, very big time, after all those billion operations, at that big time t, if I say this is a possibility, then this is something that could well be true at this point. It's conceivable that this is true at this point, at that point in time, regardless of how things happened in the past. Okay? So this can indeed manifest. So this is consistent with the run that has happened thus far. That's what a possibility captures.
I'm still struggling to understand. Imagine you have a lot of NQ operations preceding
Correct.
this fragment, then the state would have a lot of elements.
Correct. State would have whatever it has. If there are million items, it would have million items, but maybe there were also DQs as a result of which Q has only 2 elements, it would have 2 elements. And in one state, it could be 2 elements. In one possibility, it could be 2 elements. In another possibility, it could be 97 elements, just like we showed here. But then the possibility still encodes only information about the possible state of the queue at that point in time and the possible status of each of the processes at that point in time, where the status of a process only reflects the status of the ongoing operation of that process at that point in time. It may have executed billion operations in the past, but none of it is present in the summary of what a possibility conveys. Yeah, Yeah. So Ula's question is, this is a possibility that corresponds to NQ9 linearizing before NQ5. And there is another possibility where NQ5 linearized before NQ9, and that I didn't have that possibility on the screen, but if I had it, it would have the same stuff for these 4 rows, and here it would be 5, 9, right? In particular, if you imagine that there were a couple of DQs as a result of which, I mean, they were taken out, then those 2 runs, which are different runs, would have led to the same possibility. So when you look at that possibility, you don't know how you got to that possibility through that run or through this run. Okay? I'm saying it doesn't matter. This is all we choose to remember. Make sense? Okay. So the possibility set currently, currently we showed 6 possibilities, and then there are more which we have not bothered to show. But whatever they are, that's the set of possibilities. So now, let's say we advance to a greater time t2. Okay? And let's say before the time t2, the DQ operation by pi4 has completed, while the NQ operations are still ongoing. Now at this point, of the possibilities that you see on the screen, some are no longer tenable. Some, these possibilities no longer are possibilities. Okay? Only these 2 continue to be among the previous possibilities. Only these 2 continue to be possible, and this reflects that pi4 DQ'd the 9 that pi2 had NQ'd, leaving the Q with 5. And this reflects the fact that NQ5 has not linearized yet. NQ9 was linearized, and that 9 was taken away by pi4. But it is a slight lie that these can be possibilities at that point, because DQ has already completed and left, right? So the status of pi4 does not any longer have an ongoing operation. So really the status of pi4 at this point is blank, blank, blank. It has no ongoing operation, right? It reflects the fact that pi4 and pi3 have no ongoing operations at time 2. These are possibilities at time 2 now. Pi3, pi4 have no ongoing operations. Pi1 and pi2 have both linearized, and 9 was taken away, removed by pi4. So the Q state is just 5. So that is a possibility. So the set of possibilities, of course, is dynamic. As the algorithm executes and as the algorithm carries out steps, the set of possibilities is also changing. Okay? That we understand. The notation that you will keep seeing, and therefore let me just explain it here. We use the letter capital P for set of possibilities, and we will use lowercase p or p prime, things like that, for an individual possibility. But what's the structure of an individual possibility? Think of an individual possibility P as a tuple, where one component is state, as you know. You saw those rectangular boxes. One component is the state, and the state is the abstract object state. By that, what do we mean? We are trying to prove the linearizability of the implementation of some object. So what the state of that implemented object is. What is a possible state of that implemented object? That is what is communicated through p dot state. And what does p dot pi for each process pi have? It's a triple, which is operation, argument, result, response. And if there is no ongoing operation from the process pi, then the triple is going to be blank, blank, blank. But if there is an ongoing operation op from that process, and op's argument is arg, but this ongoing operation has not linearized yet, then the third component is going to be a blank, as you know from those illustrations. On the other hand, if the ongoing operation has even linearized, then this will be non-blank. Of course, there may be operations like dequeue or read that have no argument, in which case, I mean, the second component will be a blank. So that's our notation for nothing interesting, important going on here. Okay, core idea. Before we go to the core idea, any questions on the intuition behind what a possibility is? All of it is good. So here comes the main thing. So how do we? I mean, we know by now that the possibilities keep changing with time, right? As the algorithm executes each step, the set of possibilities can keep changing. So how do you track? How do you track all these possibilities, right? So to track all of these possibilities, we are going to initialize the set of possibilities in a very reasonable way, which is a very straightforward way, you will see, very straightforward. And then we have 3 update rules, how to update the set of possibilities as each step happens in the algorithm. Okay? So the 3 update rules are, the first rule is, how should you update the possibility set when a process pi invokes an operation? The second rule talks about how to update the possibility set when a process executes a step of the algorithm. Like, I mean, a process already invoked, let's say, the procedure NQ, and it's executing, maybe the procedure NQ has 100 steps, and it's executing one of those 100 steps. And when it does that, how do you update the set of possibilities? And the third update rule tells us about how to update the set of possibilities when pi returns from an operation by returning some value r. Okay? So how do we track possibilities? By thinking reasonably about how to initialize the set of possibilities and what to do when any of these steps happens. Of course, in an execution, any step that happens is going to be one of those 3 kinds. And therefore, this is an exhaustive set of rules for how the set of possibilities is maintained. Okay? So now, what is the initialization? Well, what do you expect the initialization to be? You tell me. What do you? I displayed it. How many possibilities are there in the beginning? Just one. Just one, because only one possibility, right? The object is in some state, and all the processes are idle. They have no ongoing operation. So a possibility that reflects that the state of the possible state of the object is the initial state that you intended for the implemented object, and that every process is idle, has no ongoing operation, would describe the only possibility initially. Yeah, so initialize the set. So again, recall that capital P is the set of possibilities that we are tracking, and initialize that set with just a singleton, with a single individual possibility. And how is P naught set? P naught dot state is the initial state that you intend for the implemented object, that you wanted for the implemented object. And P naught dot pi for every process pi is blank, 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 because no process has an ongoing operation yet. So that's easy. So now the 3 tracking rules. The first one is very easy. So that's the first rule, the first update rule. The first update rule has to do with what do I do, how do I change P when a process pi invokes an operation op with an argument arg. So what should we do? We should take each existing possibility before the step and then simply update P dot pi. I mean, if pi is invoking this step now, then what was pi status just before it invoked that step? It must have been idle, bottom, 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 blank, blank, blank. So change P dot pi from blank, blank, blank to operation argument, and it's still ongoing. It has not completed yet. Therefore, op arg blank. Clear? And underneath that, I'm just expressing this truth in a slightly more formal way because the set of possibilities is a set and I'm expressing it as a set. Okay, this is restating this. So update rule 1 is already out. Initialization is out, update rule 1 is out. Now update rule 2 is interesting. Update rule 2 is about what? It's about a process pi executes a step of the algorithm. When a process pi executes a step of the algorithm, then what could happen to the set of possibilities? I'll wait for a minute or two so that you can all think about it and give me a suggestion. Feel free to talk to each other, brainstorm together. Some of the possibilities become impossible. Maybe they do, and maybe some new possibilities become possible, but how should I update it? Very good. I mean, if you know the algorithm and if you know how the algorithm works, you might be able to tell that when this step happens, nothing interesting happens. I mean, in terms of at least the possibilities. Every step, I mean, is interesting because presumably if you remove it, the algorithm will be incorrect. So no step is uninteresting unless the algorithm is kind of loosely written. So, but that's not what I mean. The step might not be too interesting in terms of affecting the possibilities. That's possible. Or maybe the step is going, but that will depend on an understanding, a very critical understanding of the algorithm. But we have no algorithm in front of us. We are trying to develop a method that works regardless of the algorithm. So here is the important observation. That's what you are saying. Very crucial insight is when any process takes a step, any subset of the ongoing operations that have not linearized yet can now linearize. Let's say there are 100 of us here, and let's say 20 of us are idle and 80 operations are ongoing. Of the 80 operations, let's say 30 operations have already taken effect in a particular possibility. So in this possibility, 50 of the operations are still ongoing and have not taken effect. And then some pi out of these 100, out of these 80 active processes took a step. So that process pi taking that step can potentially lead to any arbitrary subset of the unlinearized ongoing operations to take effect in any arbitrary permutation. That's a possibility, right? That's a possibility. It could happen that way.
Any subset or just one, but arbitrary one?
So if there are 50 unlinearized ongoing operations, then there are 2 to the 50 subsets. Each one of those subsets, those operations can take effect. But suppose your subset, I mean the subset you are looking at has 40 operations in it. Then those 40 operations can linearize in 40 factorial ways, right? So you have 2 to the 50 sets to potentially work with. And if you consider any particular set, let's say of size k, there are k factorial ways of permuting that subset. And I'm saying that all of these are possible. That they are possible is undeniable. I mean, it may be unpleasant to you that there should be so many possibilities and that we should want to consider them. That's a different matter. Don't worry about that. But you cannot dispute the fact that that is a possibility. Are we together?
When you say possibility, do you take into account the sequential specification of the object?
Correct. The object has a sequential specification. Therefore, for instance, suppose the subset has the 3 of us, And let's say the permutation we have, permutation you have in mind is you, she, and I. And so in the possibility, just before the step, there was a state for the possibility. Now to that state, apply your operation, and then her operation, and then my operation. That would result in a particular new state, and that would also have given you a response, her a response, and me a response. So now consider the new possibility, which is the old possibility to which this particular permutation of the unlinearized ongoing operations has been applied. So this new possibility will be in the new set. But there would be such a new possibility corresponding to every old possibility and every subset and every permutation of the subset being applied. Okay? Do not worry about the size of the possibility set, because sometimes, it is so disheartening to visualize the size of that set that we sink. And thing is, we don't care. Why do I say we, if foreseeing that it is worrying you, I want to say one thing. In the end, are we going to run this algorithm and actually maintain in the computer's memory the possibility set? If you do that, any computer, even one developed million years later, will crash probably, okay? Because it's beyond the number of atoms in the universe probably to maintain this set. We are not physically maintaining this set. This is a conceptual set that's being maintained. Now look at the set of integers. How many are there? Lots. Can we not make intelligent arguments about integers? The fact that it's an infinite set has not stopped us from exploring and making very interesting theorems about integers. Real number set, it's uncountable. Are we not able to make arguments about real numbers? We can. Likewise, the bigness of the set is not a deterrent to what it is that we want to do with it, because we are not going to physically maintain it. We are only going to reason about it. So long as your reasoning is manageable, then this is not a deterrent. Are we together on that philosophical view? Okay. So now, yes.
How are we going to use this set of possibilities later?
How are we going to use the set of possibilities later? That will come to you in something very interesting. That will come in just a few minutes. Okay? Okay. So the rule 2 is about to come now, that which we just said, what it will be. So when any process pi executes a step, each possibility little p in the current set is going to be, so the new set p, so I'll denote the new set by p prime. P prime is just what p should get updated to. So each possibility p in the old set is updated to reflect that any set of pending operations, meaning any set of operations, ongoing operations that are not linearized yet in that possibility p. So that any set of pending operations can linearize in any order. So that's a crucial rule, this rule 2. Okay. So saying that in a little more detail, more precisely, let pending p be the set of processes which have an invoked, meaning ongoing, unlinearized operation in the possibility p. So in pending p, let pending p be the set of all processes that have an unlinearized ongoing operation. Okay? And now let S be any subset of pending p and alpha be any permutation of that set S. And let alpha p denote the resulting possibility, the result of applying to the possibility p this sequence of operations alpha. And now that new possibility p prime, which is alpha p, is going to be thrown into the new possibility set P prime, which is what the set notation here says. I was told that if I go there, I'm not getting recorded, so not to go there, but I'll go there briefly. The new set P prime is going to include a possibility P prime when, if there was a possibility P in the old set, and for some subset of pending operations in this possibility, some permutation of that subset would cause the old possibility to become the new possibility. Okay? So, include all such possibilities P prime, and that would be your new possibility set.
Prasad, what do you mean by executing a step precisely?
So, your algorithm, let's say you are implementing a queue. You have a procedure NQ, a procedure DQ. Your procedure NQ, let's say, has 10 instructions, 10 atomic instructions. Execution of each, a step is an execution of an atomic instruction of the implemented procedure.
Imagine that you executed DQ operation, then there is a read step.
Yeah.
For example, in this example.
Correct. Correct. You read X. So there's a read step. So when anybody executes a read step, all of this will happen.
Yeah, but if you read specific value in the array, that might mean that there's only one possibility which is updated. Maybe some subset of those possibilities, not all of this reordering.
How are you so sure?
Well, because you associated the read value with this step, right?
Yeah, yeah. No, this algorithm is an unknown to us. Maybe the algorithm is such that I'm not taking any particular example like the read step, but at the step that you performed, maybe that was a key step by the performance of which suddenly some operations that are ongoing become linearized right there.
You're explicitly agnostic to the algorithm. You just say
I'm completely agnostic to the algorithm, right? Because you want your method to work regardless of the type of the object being implemented, regardless of the trickery and the sophistication of the algorithm or the lack thereof. You want it to be universally applicable. So what I am saying here is indisputable. In the sense that I'm saying I'm ready to face the possibility that any subset of ongoing unlinearized operations can linearize in any order at any point in time during the execution. So you could question me on such a liberal policy, but of letting so many things happen. But I'm saying, any of those things, can happen. So I'll take that into account. Are we together? Okay. So you will also agree that because of this rule 2, several possibilities, any algorithm, take for instance Herlihy-Wing algorithm. That Herlihy-Wing algorithm was conceived by them, crafted by them very carefully to work in certain ways, right? And if you look at an execution of their algorithm, things are going to linearize only in particular ways. As Peter was saying, there may be many steps, the execution of which would not suddenly cause the linearization of some arbitrary unlinearized operations, right? So many of the possibilities that we are throwing in are probably trashy in that sense, in the sense that they are possibilities theoretically, but they are not going to contribute to the linearizability of the algorithm. So you could have lived without them. You threw in many more possibilities than you really needed to, you might say. True. Because I don't know anything about the algorithm, I threw in all the possibilities. But there are moments in the execution when, if I threw in some junk possibilities about which I need not have cared, then there is a way to filter them out, and that comes in the next step. So this is the third update rule, and this third update rule is when a process pi returns a particular value r in the algorithm for the operation op arg that it has executed thus far. And what do you think we do there? If the process pi, let's say, is returning 5, then all of the possibilities, then any possibility in which it is not returning 5 can immediately be filtered out and thrown out of the set, because the truth is that it is returning 5. So anything that the possibility set currently contains that is not consistent, that's not consistent with the truth is filtered out, is eliminated from the set. So this is a very important rule that helps you shrink the set too. The previous rule, is helping you grow the set, and this is an important rule where you will throw things out whenever you see whenever you have a witness whenever you have evidence that they don't belong to the set of possibilities, because you are seeing truth right in front of your eyes that that possibility is not consistent with what is transpiring in the run. So for each possibility p, if p dot pi is the guy that's returning, so if for that process in that possibility the response is not r, if it's either blank or if it's something different from r, then that possibility p is not consistent with what has actually happened in the run. Therefore, throw it out. Okay? So that is how the new possibility set is built at that third step. So the new possibility set will have a possibility p prime when if there is an old possibility p that is consistent with the truth. That's it. Those are the three update rules, and that's the initialization, and that is how the set of possibilities p is maintained. That discussion is complete. What I have not answered yet is Ula's question. Okay, you are maintaining the set of possibilities, but so what? What is the use of it? Any questions? Yes.
Isn't a set of possible operations infinite?
Set of possible operations?
Infinite, because, for example, if I have Q, I may make several different NQs.
You can do NQ1, NQ2, NQ3.
Yeah, so
Yeah.
can we use it?
Yeah. So, yeah, you are right. It can be, but that does not bother us. You're smiling because I don't seem to be bothered about anything. But I'm saying it doesn't bother us because it truly doesn't bother any of us.
So when should we stop?
When should you stop?
Yeah, calculation of a possibility.
No. So P is a variable. Think of P as a variable, capital P, the set of possibilities as a variable. So you have your original algorithm A. So augment that algorithm with this variable P. So add this extra variable P to that algorithm. And as a step, as the original algorithm carries out a step, along with the step of that original algorithm, imagine P also being updated according to the rules we stated. Okay? So now that is a new algorithm, right? So that brings us to the, so how we track all possibilities? Well, initialization and the three update rules that we just went through. So the main theorem, so let A star be the same algorithm as A. Suppose A is the algorithm whose linearizability you want to talk about, you want to prove or disprove or whatever. So let's say A is the algorithm whose linearizability you want to prove. transform A into algorithm A star. What is this algorithm A star? Algorithm A star is the same algorithm as A, except that it is augmented with this variable capital P. And at each step, capital P, along with that step, capital P is atomically changed. Imagine that capital P is also atomically changed. Again, this is not an algorithm you run. So don't worry about how can I atomically run that and this. Just imagine doing that. So with a variable P that tracks all of the possibilities. So are we clear about what this algorithm A star is? A star is the original algorithm A equipped with this extra variable capital P, which is updated with each step of the original algorithm as we just explained. Now, what is the connection between A and A star? Here is the connection theorem. A is linearizable if and only if the set is not equal to the empty set, meaning the set never becoming empty. That's an invariant of A star. So you are maintaining the set of possibilities, right? So if the set of possibilities will never become empty in any run, then your algorithm is linearizable. Conversely, if your algorithm is linearizable, then this set will never become empty in any run. So that is the use of this set. Okay. So what does this mean? This means that if someone gives me this algorithm A, for example, Herlihy-Wing algorithm A, and asks me, hey, is this algorithm linearizable? Then what do? I instrument it with this new variable P and update it like I said, and consider that new algorithm A star. And now I have the new algorithm A star. A star is the instrumented A. Now I have this new algorithm A star. So I can now write invariants for this new algorithm A star. And so if this is an invariant of this, if the simple statement that P is non-empty is an invariant of this algorithm A star, if I can show that that is an invariant of the algorithm A star, then I have shown that their algorithm is linearizable. Furthermore, if their algorithm is linearizable, then they surely will be an invariant of A star, and therefore my method will not miss. It's not like, oh, sometimes it's able to show linearizability for some algorithms it cannot. No. If that algorithm is linearizable, I'm sure to be able to show it to be linearizable because this is sure to be an invariant of A star. So long as I can show that that's an invariant of A star, I'm not missing the fact, truth. Is the theorem understood? I'm not going to go into the proof of the theorem. Proof of the theorem is not difficult, actually. I mean, it is. But because we have not missed a single possibility, the completeness is guaranteed. We will not miss the linearizability of A. Had I been selective about what possibilities to keep and what to kind of dismiss, well, I could have missed. I could have made the set empty through my indiscretion. Okay, very good. Any thoughts or questions? Yes. What is A star? What does it mean to say something is an invariant of A star? Okay, a very good question. I should have said that. When you say, take any statement, for instance, P not equal to empty is a statement. When you say it's an invariant, what it means is, when you run this algorithm A star, do you agree that P keeps changing? And it also depends on the run. There are several runs, and in each run, as it progresses, P is changing. So if you say that is an invariant of A star, it means that at every point in time and in every run and at every point in time in that run, P will be not empty. So if that statement holds at every point of every run, then you say it is an invariant.
P is the set of possibilities.
P is the set of the possibilities.
Okay.
So if the set of possibilities never empties out, and that is so in every run, at every point in every run, then we claim that the original algorithm A must have been a linearizable algorithm.
Yeah, but when you run the program with more functions being finished, the possibilities are shrinking. So in the end,
The set of possibilities, it might grow, it might shrink. If it ever shrinks to the point of becoming empty, that will happen only if your algorithm is not linearizable. That's the claim. That's what we are stating as a theorem, which of course has to be proved. But I'm saying it is intuitive in the sense that since I'm not missing out on any possibility, well, here is the intuitive proof. Take any run of the algorithm up to any point in time. Okay? If that run was linearizable, then just imagine the possibility you would have been left with if you started with the initial possibility and went according to the run. So that possibility would surely be in the set, and therefore the set would not be empty. That's not a proof, but there's a formal proof, but you can argue it out. You can intuit on it, and then you can look at it.
Can we really show this property for potentially infinite number of threads in practice?
Yes. For example, the Herlihy-Wing queue, which we proved correct, is an algorithm for an arbitrary number of threads, meaning you don't know how many processes will access it ahead of time.
Yeah,
it can be any number.
But will we be able to prove that the set of all possibilities is always non-empty?
Yeah. So think of it at this point. So his question, as I'm sure the rest of you probably heard or didn't hear, is that if there are, let's say, an unbounded number of processes, we don't know ahead of time, let's say, how many processes are supported by the implementation, as is the case with Herlihy-Wing's algorithm. So, this set P is explosively big. And in such a situation, when you have infinitely many processes or unboundedly many processes, can you argue about those algorithms, and will you be able to show this to be an invariant of A star? That's the flavor of the question. And the answer is, forget about showing it with a machine. How would we as human beings show that something is an invariant of A star, or something is an invariant of some algorithm? You will look at that algorithm, and then you will write out the invariant of that algorithm, which states, that requires a lot of insight, by the way, to write the precise invariant of the algorithm. And of course, you want that invariant to be strong so that it is provable by induction. So it has to be an inductive invariant. So you arrive at the inductive invariant, and then you write the induction proof, right? And then you write the induction proof. And so it does not matter how many processes there are, you will be able to, as a human being, write an induction proof. And she, as a human being, if she has the patience, can go through your induction proof and your complex inductive invariant and verify that indeed you performed your induction proof correctly. The fact that natural numbers is an infinite set has not stopped me from being able to prove theorems about natural numbers. Likewise, the fact that there is a very explosively big set or possibly even an infinite, not an infinite set, P never grows to, anyway, whatever that set size is, does not come in the way of you being able to make a qualitative argument about it and someone else being able to verify your qualitative argument about it. And make sense? So that's very good. Yes. If and only if, correct.
Yeah. And second question, you wouldn't adjust the notation for making possibilities. This notation, I guess, could be applied to non-linearizable algorithms which have mistakes in them.
Correct. Suppose your algorithm A is not a linearizable algorithm. Suppose it has some kind of an error and it's not a linearizable algorithm. Then you can build A star for that algorithm, and then you will never be able to prove that that's an invariant of A star. You can attempt to prove that that's an invariant of A star, but you will not succeed.
But I mean, at which point this notation rejects invalid possibilities that are not linearizable?
It's not giving you a decision procedure to say yes, it is linearizable or no, it is not linearizable. But it is giving you a method for how you could verify the linearizability of A. If you succeed in this, you know A is linearizable. But if you started with an A that was not linearizable, then you will have a lot of sorrow, pain, trying to prove that this is an invariant. You will never be able to do it. You might never know when to give up. So I'm not claiming that there is some point in time when it will become clear to you that that's not an invariant.
But I mean, does the notation know whether some possibility is linearizable or not? You are saying the notation doesn't have a notion.
I'm only claiming that what you see there. If A is linearizable, this is going to have that invariant. If A is not linearizable, then P not equal to empty set is not going to be an invariant. That's all we know. How we take advantage of it is up to us, but that's all being claimed. So it is not giving you a decision procedure for, I'm not claiming that there is a decision procedure to which, you can feed in your algorithm and then that decision procedure will terminate and tell you it is linearizable. You are not asking for it, it looks like, okay.
Imagine we have a non-linearizable algorithm, and we have an example of sequence of steps in which it's obvious that that's because it's not linearizable. But I mean, the sequence of steps still fits the notation. Stack. And I don't know. I guess this single example isn't enough to prove that the subset is not empty at all times. But okay,
I think what I was able to get from your scenario is that suppose you have an algorithm that is clearly not linearizable, that's not linearizable, suppose. Then what this is saying is, if that's not linearizable, there will surely be some execution of that algorithm where if you keep computing the possibility set like I said, there comes a point at which your possibility set will become empty. Okay? Which is the same as saying that P not equal to empty is not going to be an invariant.
How to find this run? We can't build these infinite possibilities. We haven't enough memory.
Okay, okay. So, so there are two things. Right? One thing is, at this point, all I want to be sure is that we understand what the theorem is stating. And then it looks like, I mean, you are wanting to use this theorem to do some useful things. And then you have questions related to that. We will come to that in a second, in a minute, whatever. Okay. But before I get to what you say, notice this. Partial tracking may suffice sometimes. We tracked all of the possibilities before. Like we threw in all the possible ways in which linearizations could happen and threw that into the set P previously, right? But sometimes when you design an algorithm, for instance, I mean, when they designed their algorithm, they would have a lot of intuition about why that algorithm is correct. Like for instance, they might know ahead of time that DQ is going to linearize at this particular point in the execution, and it's not going to linearize anywhere else. And NQs, I mean, will linearize either here or here. I mean, they may have some clear understanding of how things are happening in their algorithm. So when you have that knowledge, there is scope for using that knowledge as opposed to blindly letting the set P incorporate all of the possibilities. So you can do partial tracking if you know what possibilities, if you feel you know what possibilities to keep track of and what possibilities to not even consider, you are free to do that. And what does that mean? So for an algorithm, I mean, this is what we saw. At the moment, I mean, in what I have said, we kept track of all possibilities. And when you kept track of all possibilities, what kind of a theorem were you able to get? You could get a theorem that this statement A is linearizable is equivalent to this statement that P naught equal to phi is an invariant. It's an if and only if statement. But on the other hand, if what you keep track of is not the set of all possibilities, but you only keep track of some possibilities, then you get a weaker theorem. And what does the weaker theorem tell you? It tells you that, look, if you are able to show this invariant, then the algorithm is linearizable. It's one direction only, right? So if you are able to keep track of possibilities decently enough that you are able to show that P naught equal to MT is an invariant, then you can be sure the algorithm is linearizable. But if you are only keeping track of some possibilities and those possibilities became empty at some point, it could be because you didn't take care of the rest of the possibilities that were also crucial. So obviously you don't have the theorem in the other direction, but you also have this theorem. So why might this theorem be useful? As I said, if you as the designer of the algorithm know where the linearizations are happening, you can incorporate that knowledge into how you keep track of the set of possibilities P. At other places, you won't indiscriminately throw in all the possibilities. You throw in the possibilities that which you know are possibilities that will lead to linearizability. And when you do that, so long as you can show that the resulting set satisfies this invariant, then too you have the comfort of being certain that the original algorithm A is linearizable. So, and how do you keep track of only some possibilities? Well, initialization rule, the rule upon invocation and the rule for return, they remain the same. The rule for executing the step was that you throw in all the possibilities and you let P prime be that set. Now, if you only want to keep track of some possibilities, the only change is instead of keeping all of these possibilities, you are free to choose any subset of those possibilities. Okay? It's completely up to you what subset you choose. If you inappropriately select your subset, then I mean you won't be able to prove that it's linearizable, but you are free to select. So you are free to partially track, and even with your partial tracking, you are still able to show the invariant. Great. That too amounts to proving the linearizability of the original algorithm A. Okay. So, finally, how will all of this help with getting the machine certified proof of linearizability? That's it. So, let's say this is your software proof assistant. In our case, we used TLAPS, TLA proof system. So let's say this is TLAPS or some other software proof assistants. And let's say this is an algorithm A whose linearizability you are convinced of. You designed it and you know it is linearizable, but you want to prove that it's linearizable. Then what do? You transform this algorithm A into A prime for A enhanced with a partial tracker, or A star, which is A enhanced with a full tracker that takes all possibilities into account. So you transform this into A prime or A star and feed that into the TLA plus system, meaning you describe the algorithm in the language of TLA plus. And in addition, what do you want to prove? You want to prove this statement P not equal to empty as an invariant. Typically, I mean, how to prove that something is an invariant, you will have to strengthen the invariant so that there is an inductive proof for it. So you have to come up with typically a stronger statement, but your stronger statement in should be such that P not equal to empty is one of the conjuncts of your invariant, so that if you proved inf, then that automatically means that P not equal to phi is proved, empty set is proved. So you take your instrumented algorithm, you feed that, and you feed the inductive invariant. Who is coming up with the inductive invariant? You, potentially the designer of the algorithm, with a lot of effort. It takes a lot of effort to come up with an invariant for an algorithm, intellectual effort. You put that in. So it's a lot of work, but you do it. Of course, it's a lot of work to prove any algorithm. So you are not exempted from that work. You still have to do it. So put that invariant in. And then you want to convince this fellow that this is indeed an invariant of that. So to convince this fellow that this is an invariant of that, you write an induction proof that this is an invariant of this. And you feed that induction proof into here. These are things, by the way, writing an invariant and writing an induction proof is something that we do always, except that we do them with paper and pen. This time, you are feeding them to the proof assistant. Okay. The proof assistant is adept, it's good at being able to verify such invariants, simple invariants. It can do that. So if it is convinced that your proof is correct, that this is an invariant of this, it will say, yes, I am convinced that that's a proof of this invariant. And if it says that, by our theorem, what does it mean? It means that the original algorithm A, of which this is the instrumented version, that algorithm A is linearizable. So if I, for instance, want to prove Herlihy-Wing algorithm A to be linearizable, what do I do? What did we do? We transformed Herlihy-Wing algorithm into A prime by adding the variable P, the set P, and updating it with partial rules. And then we looked at that algorithm and we wrote the invariant for it, an invariant that implied that P is not equal to empty. And we wrote a proof of that invariant, and we came up with it with our hands and sweat. And then we fed all of these to the proof assistant in the language that it understands. And then it said, I agree that your proof is a correct proof that this is an invariant of that algorithm. And by virtue of our theorem, what does that mean? It means that their algorithm is linearizable. So this is how you do it for any algorithm that is linearizable. If their algorithm, they had an error and were not linearizable, our effort to do these and feed and get a yes from this would have failed. And therefore, we would never have been able to prove that their algorithm is linearizable. we might not have known, I mean, if we were not independently thinking that whether our inability to get this answer yes is because their algorithm is erroneous, or whether we are simply not able to do things is a different matter. But if we get a green signal from this, then that means the original algorithm A is linearizable. And that is how you can prove an algorithm linearizable. Is the procedure clear? Let me stop there and ask you for that.
So A prime is what we used to call A star, or is something else?
A star was the algorithm A with the p variable, where the p variable was updated according to the original rules that threw in it all possibilities. A prime is a notation for the algorithm A instrumented with the p variable, except that instead of throwing all the possibilities, you might be choosing to selectively throw only some possibilities. So of the 3 update rules, you still follow the update rule 1 and update rule 3. But for the update rule 2 of what to do when any process pi takes a step, rather than throwing a particular set, letting a particular set be p prime, you can just let any subset of that set to be p prime.
The proof is not, it may have false negatives, right? It may say that the algorithm is not correct, but
we will never say the algorithm is not correct, right? If you did not throw in all the possibilities that you should have thrown, you might not have succeeded in proving it to be linearizable.
yeah.
But
It doesn't imply that the algorithm is
correct.
That's what I said.
Yeah.
Does this assistant return trace of run when invariant doesn't hold? Can we see this run?
So you could potentially use a model checker to output a run in which that set becomes empty. But model checker, model checker is something that you actually run. And therefore, I mean, if the set is an explosive set, the model checker, I mean, might be of little use to you. But in principle, you can do that, right? Whereas in this whole thing, by the way, we are not running this algorithm A prime anywhere. We are not running the algorithm A prime. We are making arguments about the algorithm A prime, which is different. We can make arguments about an infinite entity and get fruitful results. We might not be able to count through an infinity.
If this soft tell us that our algorithm is not linearizable, how can we be sure that it's not bug in this soft, in checker, not in my algorithm?
Say that again.
This soft can have bugs, and it tells me that my algorithm is not linearizable.
This one?
Yeah,
This one is never telling you that your algorithm is not linearizable. When it is linearizable, you have a way of convincing it that it is linearizable. When it is not linearizable, you have no way of convincing it that it's not that it is linearizable.
So basically, if it's really true, then you know that you are a good programmer and you also know how to do all these things. If it says no or false, then you know that there is a bug somewhere, but you don't know where.
in my code or this code?
But this code is something that you write as well. This is something, right, Prasad?
Yeah. Which one? All of these? Yeah.
Parts, you have to prepare them. You have to
I see.
write them in a
But
specific
software proof
language.
is
So if this is wrong, which is probable, again, it's your mistake. So you are making mistakes at some part of your design.
Your question is
This is what I understood. Please correct me if I am wrong.
say it again.
That basically, if the component there is green, then it means that you know very well to design. You have designed correctly this algorithm, and you have applied correctly the two boxes that are there, which is to state the right invariant and to write the inductive proof correctly. So you're okay. But if this is not green, whatever it outputs, I don't know.
It doesn't, I mean, if it's not green,
Something, right? It
huh?
has to output something.
No.
false.
Software proof assistant, I mean,
It's non-conclusive.
no. When you are working with the software assistant and you feed in a proof, you are trying to convince it that a certain statement is true. And if you and you are feeding in a proof of that statement. So if your proof is incorrect, then you will not be able to convince it of that statement. So what you will get out of it is that if I wrote a wrong inductive proof, for example, then I will not be able to convince it to take it.
Okay, so if it doesn't take it, then it means that somewhere there is a bug, but you don't know where. If it is in your algorithm, if it is in
Yeah, it could be in the algorithm, or it could be in my inability to write a correct proof for the invariant. Yeah, so you can't conclude that the algorithm is wrong because it might lie in my inability to correctly write the inductive
I
proof.
also ask something. So this, I have been in discussions where these systems have been criticized that it is difficult to write the statement and the inductive proof using the specific language that the whole system requires, right? So is this true? Can you convince us that it's easy, or not easy, but you know that it's not right?
So first of all, the only software proof assistant that we happen to use is TLAPS. Okay, and whether that is the best assistant to use, or whether we should have used something, or we could have used something, we don't know. Since, I mean, we were led to that, and we started using it, and it was serving our purpose, so we persisted with it. So that's the only thing that we have experience with. And in terms of learning TLA+ and being able to express an algorithm in TLA+, or being able to express a statement in TLA+, or a proof in TLA+, we found it very intuitive. I mean, the language was not a deterrent, or it is. The proof system, these proof systems, I mean, suppose you want to convince them of some number theoretic thing that you so well know to be true. Sometimes, I mean, it's hard to convince them of things that are clearly true, because the mathematics, I mean, human brain is good at doing some mathematics, and some of these systems, I mean, they use some backend servers to do things, I mean, and if they don't get done in some quantum of time, they'll come and tell you, I was not able to verify your proof. So either you have to work with faster, I mean, more computationally intensive machines, or you may have to give it some extra facts and extra steps in your proof that will facilitate the proof checking, and things like that. So there is pain involved in proving a statement that you know to be true, to convince it of its truth. But anyway, those are all, and some other system might do it better, we don't know. But in terms of the ability to express things in TLA+, it was not difficult.
Is that under the inductive proof that is an invariant of A-tonus, basically the whole proof that you would write as a designer of the algorithm plus
the whole proof you would have written on paper.
On paper is hidden under this component.
Correct. You probably will have to. You don't. Here is an important thing. In any proof, there are at least two people involved, right? One is the human prover, the human being that's coming up with the proof, and then think of the other person as the journal reviewer, who is hit with the 70-page paper that has a 25-page proof of something, right? The human prover presumably is the algorithm designer and is very excited to come up with a proof, write the proof, and so on, and is willing to put in the effort to come up with a proof for their own algorithm. It's the reviewer's job that's miserable of wading through a 25, 30-page proof, right? Here, if you do this, you are not saving on the effort of the human prover. the human prover still has to write the invariant for this algorithm A prime, which is very intensive intellectually, and write the induction proof of this, which is probably not intellectually very a big effort, but it is voluminous and it's painful. So human prover is not saved any effort. But look at the job of the reviewer. Let's say this algorithm, is verified this way, and this algorithm comes to me in a journal paper. Okay? I don't even need to understand the proof, or I don't even need to think about what the proof of the algorithm is before I am certain with full conscience that this algorithm is correct, because it comes with a machine certification of that this is an invariant of this algorithm. And therefore, I know this algorithm is linearizable. I don't need to look at the proof at all. Even better, I don't even need to look at the algorithm to be sure that that algorithm is correct, linearizable. So I'll come to you. I'll take you. So I just need to be convinced that they produced the certification of that this algorithm meets this invariant. Once I see that certificate, I don't need to worry about the proof of that linearizability. I don't even need to look at the code of that algorithm to see what is going on. I can just be sure that that algorithm is linearizable. So it saves, so the verification is reduced to near zero. I'm not saying zero, near zero for a reason that I can come back to, but its verification is essentially reduced to zero. The prover is not spared any effort. Yeah. Yeah. By the way, I'll tell you one other thing, and I'll show you the slide. The thought was that I would do the proof of the toy example, read-write from readcast, that we would write the partial tracker and the invariants for that algorithm, which we don't have time to do. But two things. I'm happy to have that conversation with any of you who is interested to do it with that, so that you will actually see all these techniques being applied on one specific problem and to get a first-hand feel for how that goes, point number one. Point number two, if there is any other algorithm, maybe a new algorithm for me, for you, that you are potentially interested in exploring how we might actually prove that correct using this method, I'm here for one more day, and I would be thrilled to start thinking about it. Here is an example. You read X. Okay? Imagine an algorithm where you read X and you are returning X plus 1. Okay? And now, before the statement, the set was something. The set of possibilities was something. And in that set of possibilities, in every possibility, the state, let's say, had X. And when you return X plus 1, and what did that third update rule said? That if you are returning R in some step, so you are returning X plus 1 here, and that if X plus 1 is not consistent with the result part of the possibility, then that possibility is thrown out. It's eliminated.
Yeah, but why do you need to return X plus 1? You can still return X.
It was already correct.
Say that again.
Why should you only return X plus 1? Why isn't...
No. I'm just showing you one example of a non-linearizable algorithm. Like, for instance, that algorithm with a return statement changed to return of X plus 1 is an example of an algorithm which is not linearizable. It's an example. You can think of other examples, but that's an example of a non-linearizable algorithm. And I'm showing how, with that example, with the rules, the P could become an empty set. So for each possibility P, when you return a response R that is not in the possibilities response field for that process, then that possibility is eliminated, it's dropped from the P set. As a result of which, P can potentially become empty. నేను ఇంకో 10 నిమిషాల్లో చేస్తా. ఇంకా అవుతోంది, నేను ఇంకో 10 నిమిషాల్లో చేస్తా.
Yeah, sorry. Yeah, bye.
Did that make sense? Or if it did not, I will. It looks like it did not. We'll take it offline. Oh, I still have 5 minutes. I'm okay. Thank you. We have 5 minutes. That's a bright side. What do we do with that 5 minutes? No. First of all, my intent was to go back to this algorithm and then just show you what to do with it. Peter, tell me when I should stop. I'll stop. But until then, we'll keep going. So you tell me. Let's develop a partial. First of all, you have intuition for this algorithm, right? What was our intuition? Our intuition is whatever read-write object O you are implementing, that's its state is maintained in X. Wasn't that the intuition? You recall this algorithm from 1 hour ago? So X should have the value of O. Do you agree? That's the intuition. What else is your intuition? When is the read operation? I'm asking for the intuition because that intuition can guide you develop the partial tracker rather than developing this full tracker that takes into account all of the possibilities. If you have an intuition as a result of which you are able to develop the partial tracker which only takes into account possibilities that count, you know that those are the only ones that count because you have intimate understanding of the algorithm, then that set P becomes easier to argue about because you are managing it in ways that you completely relate to it as opposed to all sorts of junk potentially appearing there. And as a result of which, it will be easier for you to write invariants for that resulting algorithm. That's the reason for wanting to go with partial trackers whenever possible. So what is your intuition for where the read operation linearizes? There is only one real option where it reads X. Okay. What about the write operation?
Successful one, too.
Successful one, if cast succeeds, it linearizes at 2. But if the cast does not succeed, when does it linearize?
Just before the last successful one.
So if cast does not succeed, then between 1 and 2, there must have been another successful cast by someone else, right? And at that cast, that someone else's write would have been linearized. And when that write was linearized, you have to hitchhike and attach yourself just before that write, as if you happened and then you got immediately overwritten by that other write. Agreed? So when that successful fellow performed the cast step, not only was the successful fellow linearizing at his 2, but a bunch of others who were between 1 and 2, they were all getting linearized in that step. Okay? Now there is just one other very interesting observation and then I'll stop there. And that is, okay, let's say I read 5 here and then somebody changed 5 to 10 and I was going to change 5 to 100. I mean, I came to write 100, I read 5 and then I went here and I'm there, and during that time somebody changed it to 10. So at this point, am I linearized or not? I'm linearized, right? Because I read 5, I came here, someone has changed it to 10. So whoever changed the 5 to 10, I would have gotten myself linearized just before that fellow. Agreed?
Yes, but it's not because there's
So I got linearized. So for instance, if I now perform the cast, I fail and go, but that's okay because I'm already linearized. But while I am here, somebody could change that value back from 100 to 5, as a result of which my cast might succeed in the future, right? So if I'm here and the value of x is different from what I had read, then I should entertain both possibilities. The possibility in which I'm linearized before the fellow who is going to cause my cast to fail, but I should also remain open to the possibility that I have not linearized, to leave the option open for myself that should in future, before I execute the cast, x should be restored to the value I had read, that I would succeed. And that would become my linearization point. So simultaneously, two possibilities will have to be entertained. Anyway, those are the kinds of insights that you have when you have developed the algorithm, and it is just those insights that you will exploit in coming up with the invariant and the invariance proof. And therefore, it is just your insights as an algorithm designer that will suffice. You don't have to know some other formalism or this or that. And therefore, it is usable by a general algorithm designer with that experience. I'll stop there because I probably used up my 5 minutes.
kind of pleased.
Thank you.